and Dr. Kossett will speak a little bit about that today at the end of his webinar. We also are one of our key areas of expertise and where we provide service is in CFD modeling and simulations, as well as discrete element modeling and simulations. So between these two tools, or between these two modeling paradigms, we cover the entire gamut of flow in fluids as well as in granular solids. For CFD, for flow in fluids, we use CFD modeling and simulations to model complex systems with single and multi-phase flows, with reactions and other critical phenomena that is of interest to the process industries and engineering teams in the process industries. And we also look at things like fluid structure interaction, acoustics, and so on, which again are interesting and important for folks in the aerospace and automobile industries. And again, we extensively use both commercial tools as well as state-of-the-art open source tools to provide services in CFD modeling and simulations. And this certainly includes applications like combustion, applications like reactions with complex mixing and things of that nature. As far as granular flow modeling is concerned, we extensively utilize this technique called discrete element modeling, which allows us to understand flow, mixing, and related physical phenomena that occur in the flow of granular solids, which behave in very different ways from fluid flow. We're also able to describe complex fluid flow coupled with granular flow, like granulation processes, fluid bed reactors, and things of that nature, by combining CFD and DM modeling paradigms and running simulations through those. Again, we use both commercial tools and open source tools to provide these services as well. One of the other major areas of expertise that we have is in EFD, which is experimental fluid dynamics. We have a large flow testing facility at our India offices, and what we're able to do in our testing facility is build custom testing equipment for our clients, and we're able to provide experimental support to a number of modeling efforts that our clients may be undertaking or we have undertaken for them, and thereby providing the experimental support to process development or product development. So we are, through all these different services, able to provide what we call end-to-end process/product development solutions and services, and we are thus able to position ourselves as a key strategic partner for our clients. I would like to now move on to, with that brief introduction, to introduce our speaker today. So if we could move to the next slide quickly.
Yes.
Yes. We have with us Dr. Gopal Kossett, who is going to talk for the next 40 to 50 minutes on how we can address mixing and scale-up problems in reaction vessels in the process industries, and how you can use that to manage scale-up of mixing tanks, and how that affects product selectivity and things of that nature. He is going to be focusing on application of CFD technology to address this, because it's turning out to be one of the key tools that the engineers have at their disposal to manage scale-ups in the most time-efficient and cost-effective manner possible. Dr. Kossett leads our chemical reactor engineering practice and has many years of expertise in the design of multi-phase reactors and in reaction engineering problems in general. He has spent a number of years researching and studying and in helping engineers in process industries optimize and debottleneck many issues related to multi-phase flow in reactors. His chosen areas of expertise and interest are applying CFD and DM modeling to and simulations to address reaction engineering problems in multi-phase reactors. So with that brief introduction to Dr. Kossett, I'd like to turn the floor to him and he will spend the next half hour to 40 minutes on talking about how to address mixing and scale-up problems. At the end of his uh, talk, we will have some time open for questions, and at that time, I will return and then help moderate the question answer session. With that, Dr. Kost, please take over. Thank you.
Thank you, Moti, for a good introduction. Good morning, everyone. This is Gopal Kasit from Tridiagonal Solutions. Moti has given a very good introduction, so thank you, Moti, for that. So today we will talk about how we can address the mixing and scale-up problems which are observed in various processes, and what are the different ways to address those, and how we can make use of the computational fluid dynamics, that is CFD technology, to get more in-depth understanding of what is happening inside the vessel, and can we use that technology or the results obtained from that to improve our processes and make sure that we have good scale up, good tech transfers without any mixing issues, or we can get rid of the mixing issues during our scale up or tech transfer. So to understand this, let's first understand what is mixing and why mixing is very important in process industry. So to understand this, let's understand what we are trying to do in a process industry. So all our aim are, we are trying to convert a raw material into a value-added product, and this we do through some chemical or physical transformations. And while doing this chemical or physical transformation, we need to bring two or more phases component, like two or more liquid, a liquid or a gas, liquid or a solid in close contact, so that there is a transfer, mass transfer between these phases, and then we can get the desired reactions or the conversions using that. And for this we need to mix these two phases uniformly or have a good mixing. So what is mixing and why it is important in the process industry? So mixing is reduction in inhomogeneity to achieve desired process results. Inhomogeneity can be in terms of concentration, or can be in terms of phases. So where we are trying to do mixing of gases in liquids, or dispersion of gas in liquids, or dispersion of solids in liquid. There we are talking about mixing of reducing the inhomogeneity between the phases. And when we are talking about like blending of different miscible liquids, we talk in terms of reducing the inhomogeneity in concentration. Or there can be processes where we need to make sure that the temperature are uniform, either we are using a jacket or a coil, so the temperature heat transfer from that is uniform, and then we are getting a uniform temperature across the vessel volume to get the desired process result. And what we are aiming at, to get efficient heat and mass transfer, reaction rates, or good product properties. If we do not account for mixing, or do not look into the mixing issues, what could be the impact? And these are being estimated and reported in literature. So we can end up in getting low yield, poor selectivity, if we do not look into mixing issues or make sure that we address them while we do the scale up or tech transfer. We can get wide particle size distribution when we are working with crystallization or polymerization processes, where either resin beads are being formed or crystals are being formed. If the mixing is not uniform or are not homogeneous, then we can end up getting a very wide particle size distribution, which may be undesired many times. Similarly, when we are talking working with bioreactors, we need to have uniform gas distribution, and inhomogeneity in that gas distribution may lead to may impact our process, like oxygen transport to the microorganisms and nutrient transport to the microorganism, which will hamper their growth and hence will hamper the process output. So we understand why mixing is important. Now let's try to see what are the various ways we can use to perform these mixing operations. So just listing few methods which are available. So we can do mixing in batch, so where we take different components in a vessel and then mix it for a certain period of time to get the homogeneity. Or we can do continuous mixing, like in inline blending, where we are using either static mixers or some internals in the pipelines to make sure that we divert the flow path and get the mixing of various components. However, when it comes to process industry, batch mixing is being widely used, and stirred tanks are being used very widely to perform this batch mixing operation. So today we will be talking about mixing in stirred tank and then how to address these issues using CFD methodologies. So when we talk about mixing in stirred tank, let's understand what different types of mixing operations we perform uh, in the stirred tank. So I typically categorize them into two main category, that is like single phase mixing or multi-phase mixing. Single phase mixing is like we are mixing miscible liquids, where we are trying to make sure that the difference in the physical properties are addressed, like we are mixing liquids with two different viscosities or two different densities, and we are trying to make them uniform. So trying to, let's say, in crude oil blending process, we get different crude oils, and we try to mix them using impellers or jet mixers in the large storage tank to make sure that we get the uniform density, because the crude oil, different grades of crude oil will have different density, and we are trying to homogenize them. So, and in this process, what design parameter we should be looking into is typically the what is the blend time, what is the mixing time. So how long should I mix so that I get the uniform properties, physical properties. Next is multi-phase mixing, and those include like mixing of immiscible liquids, mixing of gases or dispersing gases in liquid, suspending solids in liquid, and many times we come across gas liquid solid mixing, that is where all the three phases like gas, liquid and solids are involved, and we need to make sure that the system is able to handle all those. So let's talk about now mixing of immiscible liquids, which the process typically we are trying to apply when we prepare dispersion or emulsions. And there one of the important parameter is to estimate what is the droplet size distribution of the dispersed liquid so that the emulsion is stable. Next is gas liquid mixing, which is typically encountered in the reactions where gas and liquids are involved, or in fermentation processes where uh, air in term to get oxygen is sparged in the vessels to get oxygen to the microorganisms. And one of the critical parameter or design parameter there is mass transfer rates, which we need to make sure that we get enough mass transfer from gas to the liquid so that there is a proper conversion of the process. Similarly, when we look at solid liquid mixing for dissolution, precipitation and crystallization process, we are trying to estimate suspension levels. Are the solids uniformly suspended? Are they sitting on the bottom, or are they uniformly suspended, so that their interfacial area is available for various transfer processes. And we typically look at the critical impeller speed for solid suspension, that is the minimum impeller speed we should operate with so that the solids are suspended off the vessel bottom, or many times we need to look into if the solids are uniformly suspended throughout the vessel volume or not. Similarly, in gas liquid mixing processes, we need to look into both the gas liquid mass transfer as well as solid suspension. So we look at that, okay, these are the various different processes we need to carry out, or we carry out, and various design parameters we should be looking into. But the question is how to estimate these design parameters. So what are the methods available? What design variables are available to us? So in next few slides, I will discuss about that. So we have looked into what are the critical design parameters. Now let's look into what are the design variables which are available to us we can play with or we can change to make sure that we get the right mixing parameters or right design parameters and their values. So to categorize them or to make to have differentiate them, I just use that these are the reactor hardware parameters where which are related to reactor hardware, and there are then few parameters can be like tank shapes. So we have various tank shapes. We start in a lab with a spherical vessel or a round bottom flask, and then try to scale it up to a cylindrical vessel. So we can have cylindrical, rectangular or spherical vessels. One of the most important variable is the impeller. So which impeller should be used? There are many types of impeller available. Which impeller type should be used for which processes, and how many impellers, their size, number, what should be the diameter of impeller with respect to the tank diameter, what should be the number of impeller to be used, where I should locate the impeller. So all these are the design variables which we can play with to get the right mixing parameters. Uh, One more important parameter is degree of baffling. So how should I arrange my baffles? What should be the number of baffles, where I should locate, what should be the size, and different things like that. Many times the sampling probes or dip tubes used to take samples, or thermocouples inserted, acts as a design variable. Uh, and then those also play the part of those also acts like baffle and provide hindrance to the flow. So these are the reactor hardware in terms of the what we can change in terms of which type and shape of impeller or vessel to be used. We can also play with few operating conditions. That is, one of them is rotational speed of the impeller, at what speed we should operate to get the desired results. Heat transfer rates, we can alter the heat transfer rates through the jacket or the coil, or then we can play with the addition rate. So if we are adding different liquids, should we add them slow, should we add them fast, how we should add them, what is the location of addition. So these are all our design variables which we can play with to get the right mixing parameters. Now let's look at what are the design methods available to us. So typically I categorize them into three different levels. I will first talk about level 1 and level 2 methods, and then we'll discuss about the level 3. So level 1 is, yes, we can use the general guidelines. So there are many guidelines available in literature, or being an process engineer working on various mixing operations or scaling up them, and then through years we gather this knowledge, and we can use that as our organizational knowledge to use and design our mixing systems. These can be like rule of thumbs and organizational knowledge. The level 2 methods are empirical correlations, which are derived from a lot of experimental data performed by various researchers. So we can use those correlations derived from the experimental data, and then try to apply it to our system to get the right mixing parameters, like what is the power consumption, what is the mass transfer rates, what is the blend time. We can use various correlations available to estimate these mixing parameters. However, when we look at the mixing parameters, we can see that there are, like these correlations, there are pros and cons of these correlations. So these correlations are quick design methods. These level 1 and level 2 methods are quick. We can quickly use them. We can quickly use those algebraic equations to estimate various mixing parameters, and they provide reasonable accuracy for standard systems or for the systems for which they are derived for. However, if we look into the another part, or the other part of the coin, that we see that there are also some cons to it, which are like these correlations provide us average information. They may not provide us very detailed or local information, and one of the major is these correlations heavily depend upon the impeller characteristic, that is flow number or power number. So all these correlations, if we look into, like estimation of power, we need the power number. For estimation of blend time, we need the power number or number of the impeller. To estimate the gas liquid mass transfer rates, we need the power per unit volume, and this power per unit volume will also depend upon the power number, because we need to use power number to estimate the power per unit volume. So these correlations heavily depend upon the impeller characteristic. And when we look into the non-standard configurations for which experimental data may or may not be available, I am just showing you a few designs here which we have worked through, and there was no data available. And so these correlations find limitations when we try to apply these correlations to such complex systems, because there is no experimental data supporting us for such system to use the various characteristic of these impellers to estimate various mixing parameters. So for such systems where the correlations are not applicable, what are the options available to us. So the options available to us is the level 3 methods, which are either we can use the experimental fluid dynamics so that we can go perform experiments. So we can build the scale down model, perform test on the scale down model, use various experimental techniques. Like we can use conductivity techniques to measure the blending, and then the laser Doppler anemometry or the particle velocity anemometry to measure the velocity profiles or velocities in the tank. However, performing these experiments, building these prototypes can be time consuming and can be expensive, because it will need a lot of cost involved in building these prototypes, and then a lot of time will be involved in performing experiments with these techniques. So another option is like use the numerical methods. So build computer models which resembles to your process and try to use that. So one of the method available to us is computational fluid dynamics, that is performing numerical experiments very similar to what we perform the physical experiments. We can perform numerical experiments. To perform these numerical experiments, we can quickly build uh, different models virtually. So different models can be built quickly on the computer, and then we can solve the equations, mass, momentum, and continuity equations to get the flow analysis, velocity distribution, flow distribution, and various mixing parameters. Using these models, we can build and analysis different design scenarios. So we can quickly change impeller locations, their type, and then change what could be the impact on the process, and try to understand what could be the impact of changing these design variables quickly. And one of the good part of is that we can handle non-standard conditions as well, as these will be using the physical design of the system in the 3D model. So let's look at what is involved in a computational fluid dynamics analysis. So uh, computational fluid dynamics analysis is all about solving mass, momentum, and energy equation, and steps to analyze or perform CFDR. The first step involved is we need to create a 3D CAD model or the 3D geometry of the vessel we are interested in. So using the impeller location and then different baffling arrangement, we need to create internals and baffles. We need to create a 3D CAD model. That step we called creating the geometry of the vessel. Next step is using performing meshing operation to create a mesh size where the computation will happen at each mesh point, and then performing simulation, so providing your boundary condition in terms of the fluid properties, density, viscosity, rheology models, and then converging these simulations. So converging these simulations and then extracting various data which we can use to estimate various mixing parameters from these simulations. So extracting right data from the simulation is also one of the important steps. So we need to perform all these steps to get a computational fluid dynamics analysis done. So let's see what benefits we get from doing the CFD analysis. So when we talk about stirred tank and applying CFD analysis to a stirred tank, what we get is that we can apply this method across the scales, that you can apply it to a lab scale as well as you can apply it to a pilot scale. So it can be applied across the scales. You can account, it can account for the impact of the physical design of the system, like if the baffles are placed in a certain way, we can account for that impact. If the impellers are placed in a certain way, it will account for that and will account for the interaction between the impeller as well. So if the impellers are closely placed or impellers are far apart from each other, it will account for the interaction between the impeller as well. And it provides a very quick method to evaluate impact of various design and process changes which we can make and then understand their impact. So what CFD analysis can provide us for a stirred tank is that you can understand flow pattern, the velocity distribution, and how the flow are moving for each impeller. Are they forming multiple flow loops across? We can estimate that. We can also estimate mixing profiles. We can get energy dissipation rates. that is what is the energy being dissipated, and we can get these rates locally. So what are the energy dissipation rates near the impeller or away from the impeller, we can get that estimation, detailed estimation using that. We can also get like the impeller flow number and power number based on the flow pattern generated by the impeller. So this will be when we estimate flow number and power number using CFD, it will account for the interaction between the impeller. Many correlations may not account for, or the data which is available to us from the OEMs of the impeller, they may have tested them when the impeller is operating as a single entity in a vessel under some standard conditions. However, power number and flow number are bound to change when there is an impact of other impeller or the proximity of the impeller with the vessel bottom or the liquid surface, and the power number and flow number changes from what it is reported under standard conditions. So CFD help us to derive these energy dissipation rate. It also helps us to get the shear rate distribution or strain rate distribution, which we can use to estimate what could be the impact of this shear being applied in the fluid on the particle, so that what could be the impact on this the particle size. This is a very critical parameter to understand what would be the particle size distribution in a crystallization or a polymerization process, and we will look into it as I take you through some of the examples. It can let us know in fermentation if when the gas is being sparged, what is the distribution of gas, are there any dead zones where gas is not available. It can also help us in understanding the vortex depth in systems like hydrogenation, where hydrogen is being entrained through the headspace, and the vortex, getting a right vortex and right amount of hydrogen into the liquid is very critical. Correlations may not be able to tell us this information. However, we can get these detailed information using the CFD analysis. So we have discussed till now that what are the various design parameters and various design methods available to us, and what is CFD technology and how we can apply this, or what are the benefits of this technology, what results we can get when we apply this to the stirred reactor. So in the next few slides, I will be taking you through some of the examples from my consulting experience, where we have helped client to address their mixing problems or resolve their mixing problems. So I will be taking you through some of the examples from our consulting experience, which I will use to explain how we can make use of this CFD technology to address the mixing issues. And these are from our real world experience with our clients, where we have used these techniques and addressed their mixing challenges, and the solutions proposed by us were implemented, and we have witnessed the results and benefits they got it from the solutions we proposed them. So let's understand how we can make good use of CFD technology through some examples. So, so first example is a troubleshooting example, which was posed to us like there was a vessel which was being used to get a product quality from a particular batch size. So there was a particular batch size, and then the process was going very well. There were no issues addressed. However, due to certain changes in the process or requirements, the batch size was slightly increased, and suddenly some of the process issues started, where we have witnessed issues with the product quality and the batch time as well. So batch time was significantly increased just by increasing the batch size with a few liters, and the objective was to troubleshoot and improve the mixing performance. So looking at the design, it would be obvious. One would say that just change the impeller spacing and make sure that your mixing is good. So looking at this, based on our experience, we can quickly say that just change your impeller spacing and get the good mixing out of this. However, the question is, what should be the impeller spacing? How we should space the impeller? And can we use correlations, or can we use CFD to predict what could be the best impeller spacing, or what could be the impact or can it impact negatively on the process, or can it impact positively? Can we make use of that? So we've looked into this, and first we tried to understand what correlations tell us. So we looked into the original batch, and we looked into the increased batch size, and tried to use the standard equations available to estimate the blend time. And what correlation tells us is that there is no change in the blend time, very minor change, and it should not affect the process with such a change. So that was correlation tells us. However, in actual, we observed a lot of process issues on product quality issues. So there is something going on in the vessel which we need to understand in more detail. So then we've tried to look into, can we use CFD methods to make a good understanding of what is happening. So we built the CFD model with the system, and we built the 3D steady state CFD model, and tried to look into, can we look into the velocity profiles. And when we observe the velocity profile for the original and then the increased batch, we can see that there is a good low velocity dead zones at the top region of the vessel. However, will it impact the process performance? We need to look into. We can see that, and CFD tells us that yes, there is a low velocity zones. So CFD helps us to visualize this. However, will it impact? So let's look into, try to understand, if I am adding a certain additive or chemical here, how fast it can mix in at the top surface in this system and in the increased batch. So we did try to understand this impact on the mixing performance. So we added a tracer which is of similar properties as of the bulk fluid to understand the mixing, and then try to understand what is the mixing profiles with these two. So if you look in through these animations, we can see that here the mixing is very quick. As soon as we add, it get dispersed, and then we get mixing within like 15 seconds here. So this is what is matching with what we observed with the correlation. However, when we look into this system, we see that even after the the mixing is very delayed, and then we see that it takes about 20 to 28 to 29 seconds to mix it uniformly throughout the system. And there is a dead zones, and there is a very delayed mixing in the top region. So we know that we need to get rid of this low velocity zone here. For that, again, as we have rightly said in the beginning, that we need to change the impeller spacing. So let's see, can we use CFD to what should be the impeller spacing? So let's see, there can be multiple options. I am just showing you two options which we evaluated. So we can space the impellers as option 1 or as option 2. Let's see which option works better. Can we use CFD again? Can CFD provide us good results? So we simulated it and looked into the velocity profile. When we looked into the velocity profile, we can see that there are multiple loops being formed because of the higher impeller spacing, or impeller spacing higher in this option. And when we zoom into it, we can see that the top impeller forms its own loop, and it's not talking with the flow loop being generated by the bottom two impeller. However, in the option 2, we can see that there is a complete one single flow loop being formed, and this impacts the mixing performance. Now let's see how it impacts. So in the option 1, we see that there is a very slow mixing in the top region because the impeller has formed its own circulation loop, and there is a very low exchange between these two loops. And we can see that impact here, where we can see that there is a very slow mixing here. The tracer which is added is diffusing very slowly, or moving very slowly to the bottom region, and because of that, even after 30 seconds we cannot get good mixing. However, with increased batch and with the different impeller spacing, we can get mixing within like 16 seconds, which is the desired mixing. And this, we suggested this, we have implemented this, and we have seen that the process was running even after the increased batch size by just changing the impeller spacing, making the spacing right, was able to get the product qualities and process parameters right. So this example shows us that even the issue looks small to us, and then we can say that it is obvious. However, when we look into great in-depth details of the mixing, we can see that how we can get better output from whatever the design or design variables available to us, and in that CFD helps us a great. So we can evaluate these design changes quickly. If we need to evaluate these design changes on experiments, it would take a lot of time. However, we were able to quickly evaluate this using the CFD methods. So let's look at another example, which is example from our experience where we where we were trying to transfer a suspension polymerization process used for resin bead formation from a lab scale to a plant scale. In the lab scale, when the process was performed on a small scale reactor vessel, everything was going good, and the desired particle size was obtained by fine-tuning the mixing parameters and the process steps. When the process was to be transferred, there were two options available, the reactor 1 and reactor 2, and the question was which reactor to be selected. And it may be obvious, we can say that option 2 looks good because this is our design. Option 2 looks good, but can we again estimate that a priori before transferring the process and make sure that it is transferring and giving us good performance? Can we use CFD to do that? Let's see, can we confirm and substantiate that yes, design 2 will work good compared to the design 1. So let's look at the what is suspension polymerization process and how particle size distribution can be controlled in that. So in suspension polymerization process, particle size distribution is controlled by breakage and coalescence of the polymer droplets which are formed at the initial stage of the polymerization process. Now this breakage and coalescence of the droplets depends upon the shear and strain which is applied on the droplet or which is being experienced by the droplets while they are mixing or moving in the vessel. And if these droplets spend very high time near the impeller, which is a very high shear zone because the velocity gradients will be very high near the impeller, we will get a very fine particles. And if the droplets spend more time away from the impeller, we can get coarse particles if they spend more times in the low shear zone which are away from the impeller. So can we estimate what is the amount of time these droplets spend in the different shear zones? Can we make use of this CFD? So we try to build a CFD model. So we use the CFD model to simulate flow, and then we use the CFD techniques to track the particles, their trajectories as they move from one cell to another, and track what is the shear they are experiencing each which zone and what is the time they are being spending. So we tracked many droplets, released them at multiple locations in the vessel, and tracked their trajectories and tried to understand what are the different time they spend in various zones. So we did this analysis for the lab scale vessel, the option 1 and option 2, and this is the results we get. That what this graph tells us, the percent time spent by the particle and the shear rate. We can see that for option 2, the option 1, the distribution is very broad. However, for lab scale and the option 2, we get for option 2, the time exposure history to the shear of the particle is very similar for the option 2 and the lab scale. So we can say that the design 2 will work better and then can give us performance very similar to what we have observed in the lab scale reactor. So we suggested this design, and the batch was transferred or the process was transferred. However, to understand are we giving them good suggestions, we deliberately took batches in both the reactors, and we observed that the particle size distribution was very broad in the option 1, that is the design 1, which is this design compared to the design 2. So however, though we were not able to match it very exactly with the lab scale, we were very close, and then we fine-tuned the design to make it further close to the lab scale. So this is one more example where we can say that we can apply the detail, understand more detail into the flow physics, into the particle physics, understand how the droplet spends various times in various shear zones using the CFD methods, and get a priori knowledge, a priori information of what could be the process performance, how the design will impact the process parameters, and can we get the good mixing. So we can reduce uncertainty before we transfer our process to a particular reactor. Third example is about getting the scale up right. So this was from our experience with the pharmaceutical industry, where there was a hydrogenation process being going on, and this was the actual what the process engineer did. So this was a lab reactor, and they scaled it up to a pilot reactor, 1 kiloliter vessel. The batch size was about like 3 liter in the lab, and then about 300 liter in the 1 kl. However, being the design, keeping the design same with respect to geometry similarity, the conversion was about only 30% observed in the pilot compared to what was observed in the lab scale. So if we say that it is X% in the lab, it was only 0.3 or 30% of what is observed in the pilot labs in the pilot scale reactor. Again, so can we get more detailed in-depth analysis? So let's understand what are the critical hydrodynamic parameters for a hydrogenation process. So hydrogen is being present in the headspace here, and we need to entrain that hydrogenation through the vortex formation. So one of the critical parameters is entrainment of that hydrogen from headspace through vortex into the liquid. And to make sure that once we have the hydrogen in the liquid, we disperse it properly using and disintegrate into small bubbles and get the to do that we need the desired power per unit volume ratio to make sure that we get the desired mass transfer rates. And similarly, as this is a hydrogenation process, this is being solid catalysts are being used, so we need to make sure that solid particles are also suspended. So when we looked into using correlations, we see that power per unit volume is an issue when we move from lab scale to a pilot scale reactor. So the P by V was very less. However, can the correlation did not give us any information about how hydrogen will get entrained, what would be the vortex depth, how it will interact with the impeller. uh, so we used CFD methods to do this. So we developed multi-phase models where you can see that the blue color indicates hydrogen and the red indicates liquid, and how the hydrogen is getting entrained in the liquid. And we can see that there is a lot of entrainment in the lab reactor. However, there is very few entrainment of hydrogen in the pilot reactor. So the issue is low entrainment of hydrogen in the large vessel compared to the lab vessel. So can we then try to, so what are the options available to us? We need to make sure that the design of the impeller is appropriate, and then can we make different design and compare them. So we have came up with, so how can we increase the power per unit volume? So what are the options available to us? Use an impeller with very so we can we options available to us are use an impeller with high power dissipation characteristic to increase the P by V, to increase the power dissipation. Use multiple impellers and or increase the RPM. However, we need to understand the limitations here as well. This is a glass line vessel. We cannot go beyond a certain speed. Typically 96 to 110 RPM is many times an speed limit when we are working with glass line reactors in a 1 kiloliter scale, because of the limitations in the supporting the shaft and mechanical limitations in supporting the shaft because of the glass lining on the vessel wall. So let's see, can we evolve multiple designs to address this issue by staying within the limitations of impeller speed and type of impellers which are available to us. Again, it is a glass line vessel, so we cannot use any arbitrary shape impellers. We need to stay because there is a manufacturability issue when we glass line the impellers as well. So we have came up with multiple designs options. So we have came up with few designs options keeping the baffles range, and we have also looked into can we have partial baffles. This is getting more difficult into a glass line, but still we evaluated this design, and then we looked into what could, how it interacts with the vortex interacts with the impeller, and what is the dispersion of hydrogen. So we see that in all three designs we get good dispersion of the hydrogen inside the liquid. So we can say that all these three designs are good. However, which to be selected, so we give an option to the plant engineer, and if we look into the power per unit volume predicted by CFD and the gas liquid in the interfacial area, uh, if we look into these parameters, we see that all the three designs are performing good. We were able to improve the power per unit volume as well as the gas liquid interfacial area compared to the pilot scale. Though we were not close to the lab scale, we were able to improve that. So at the end, even if we say that design B looks good, design C was selected because again it was a plant team who decided that we need to get this fabrication done with low cost, because again we are trying to prove that CFD design evolved from the CFD methods gives us good results. So this design C was implemented, and we have observed the threefold increase in the conversion after increasing this implementing this design at the pilot scale. So lab scale was about X, we were able to get it up to 80% of what is lab scale compared to what we were getting 30% with the old pilot scale. So this is how few examples I have taken you through to highlight how we can make use, how we can perform CFD analysis, read those CFD analysis, extract various results from that to make sure that we address the mixing and scale up issues during scale up and tech transfer. There are many more examples which I can share, but due to time limitations I will just browse through that. So using CFD techniques we can also understand how the solid suspension is there, how the solid suspension will change based on the velocity pattern and the impeller speed we are operating at. And there now a trend is there that in many pharmaceutical processes we use these aseptic vessels where the magnetic drives are used, and there are no correlations available to understand performance of these magnetic drives impeller, and there CFD comes in very handy to understand how will be the impact if we change the liquid level, if we change the RPM, how will be the dispersion of powder which is added from the top surface, and it will interact, how will it disperse, and what would be the performance parameters in terms of power consumption, because there is very rare data available for the impeller power number for such vessels. But however we can get CFD methods to imply and then get all these parameters there. So with this I would like to summarize that yes, we have seen that there are multiple methods available to address mixing and scale-up issues. We have our organizational knowledge as well as the correlations with us to handle the standard systems. However, they have limitations for non-standard systems. Experimental methods can be one of the options. However, it can be time consuming, and then we can use the computational fluid dynamics CFD based methods models to show which shows great potential, as we have seen, in getting detailed understanding of the mixing inside and various mixing parameters. Also it can be applied across the scales. We have seen that we can apply it to lab scale, pilot scale as well as plant scale and compare their performance across scales using these models. And this helps us to reduce uncertainty during scale up tech transfer and designing at the design stage. So what are the options available to the process engineers when we talk about performing the CFD or using the CFD models? So there are number of CFD tools available, both commercial as well as open source. So we can use many commercials as well as open source tools. And however, we need to uh, become an expert in doing various steps which are involved in the CFD analysis, that we need to make sure that we generate the right geometry, we extract the right flow domain, we perform the right meshing, and then perform the convert the simulation and extract results from the simulation. And for the process engineers, from my personal experience, I can tell that geometry and meshing are the two steps which are more time consuming. If we need to perform them multiple times, then it can be very time consuming when we do that. So is any tool available which automate the process of CFD analysis? And at the end of the talk I would like to take a couple of minutes to introduce the tool we developed. We call it Mixit. which is the enterprise tool to analyze mixing in stirred tanks. It has very intuitive graphical interface and have various features. Now, our vision behind developing Mixed is to help chemists, process engineers, and plant engineers to accelerate, address their mixing and mixing issues during scale up and tech transfer, and accelerate the scale up and tech transfer by connecting dots between the reactor, process, and product attributes. So you can understand impact between these using this tool by using correlations as well as the CFD models. And the CFD models in this are fully automated. So user just need to punch in their reactor dimensions and process conditions, and CFD simulations like are performed automated. I am just highlighting few features of our tool. So we can account for multiple impeller shapes. So we have a reactor database. You can create a database of your reactor across various plants, lab, and pilot scale facilities. You can we can handle off-centered angle multi-shaft agitators. We have a customizable impeller library, so a new impeller model can be quickly added and can be used in the automated CFD analysis process. We can handle various fluid rheologies, so various fluid rheology models are available. We also have empirical correlations and also allow user to punch in their own correlations as well. So we have both default correlations as well as facility for the user to have their own correlations as well. And then we have fully automated CFD analysis, so the process engineers can use it tool quickly to understand various details, process mixing details of in their vessels using the automated CFD. So user may not need to worry about how to create the geometry, how to create the mesh. All the steps are automated, and you get a report at the end of the simulation with the velocity contours, vectors, and then you can get that how is the mixing performance from those reports. So thank you for your patience for listening to me for past 40 to 50 minutes. I hope this session was useful to us, and now we are open to questions. So Moti,
Sure.
yeah.
Yes. Yeah. Thank you very much, Gopal, and thank you, folks on the line for listening to us patiently. We can certainly take some questions. I already have a couple that I would like to present to Dr. Coslet here. So one question that we've gotten here, Gopal, is about the time that you take that your Mixit software that you just talked about towards the end. The question is, what are some typical run times that you see with the software? Are you able to comment on that? Does it take half a day or a day or 2 days? Because this tool is automated, it'd be useful to know what kind of simulation times we're looking at.
So the typical simulations with Mixit tool are about, let's say we consider, it will vary with the reactor size. However, let's say consider a typical pilot scale vessel of 1 kiloliters capacity. So the typical simulation for time, this is about 3 to 4 hours on a quad core machine with about 6 to 8 gig of RAM.
Sure.
Yeah.
Okay. I have one other question here, a little bit on the scaling up. The question is, how do Reynolds and Froude numbers scale between a typical lab and a production vessel in some of the mixing applications that you've seen? Are there any correlations or things that you would like to discuss or, yeah?
Yeah, so I will say that we should not look into scaling the Froude number or Reynolds number. For mixing applications, we should look into scaling based on the process requirement. Like if it is a gas dispersion, we should look into how we can get. So even if we say that we keep equivalence between the Reynolds number between the lab and the pilot scale, we may not get the good mixing or good mixing parameters. So we need to look into the design parameters, which are like mass transfer rates or blend time, when we try to compare between lab and the pilot scale or plant scale vessels.
Sure. Another question, again, slightly more technical. What are your comments on using P over M as a scaling criterion in unbaffled vessels. Is that one of the important ones, or are there other parameters or aspects that we need to consider when we're looking at scaling up as far as unbaffled vessels are concerned?
So when it comes to unbaffled vessels, so as we talked about the example of hydrogenation, there are two things there. First thing is that we need to have a good vortex so that we can get that hydrogen into the liquid. Once that hydrogen is entrained, how we can disperse, or what could be the how we can get finer bubbles so that we can get maximum interfacial area, that will depend upon the power we are dissipating into the liquid using the impeller. So both things are important even if it is a unbaffled vessel.
Okay, great. So another question here. What is the direct impact of mixing on product selectivity? Is there some specific scale related aspects that we need to look at? I mean, in terms of micromixing or things of that nature. What are some of your thoughts on that?
So it depends upon the kind of process. So if your micro mixing is important, we need to look at the mixing at the molecular scale, and then the different models goes into there. However, let's say if we are trying to so when it comes to selectivity, definitely there is a reaction going on. We need to look into if that reaction is being controlled very fast, time scales of the reactions. If it is very fast, then we need to look into micro mixing issues. Or if the time scales are not too very small, then we can look into bulk mixing and see how it impacts the selectivity. However, definitely if we have poor mixing either on the micro or the macro scale, it is going to affect your selectivity as well as convergence. Because if there is a high concentration zone in certain part of the vessel, there are chances of getting the byproduct form based on the process we are trying to do there.
Okay, great. I think we are a little over the allocated time.
Yes.
So I'm going to close the session for questions at this point. Um, if any members of the audience would like to ask more questions, please do forward it to our email. I think we did share that as part of our as a web link. And then we'll be happy to get in touch with you and discuss your mixing questions and mixing needs a little bit more in detail. So with that, I believe we can bring our session to a close. I'd like to thank everyone for taking the time to attend this webinar this morning and for all the discussion after the talk by Dr. Kassett. So thank you, everyone. Thank you, Dr. Gopal Kassett, and have a great day. We will meet soon in another of our mixing webinar sessions. Till then, have a good one. Bye.
Thank you, everyone. Thank you, Moti. Have a good day.